Дорогие товарищи, сегодня у нас докладчик Амар Деббуш, профессор математики в университете Гуэльма, Алжир. Тема доклада о некоторых классах абстрактных, дробных систем, динамических систем управления. Ну, по-английски он сам classes of abstract fractional control dynamic systems. Пожалуйста, вам слово. Значит, время до часа. 50 минут.
Okay.
50 minutes.
50 minutes. Okay. Dear colleagues, first of all, I would like to thank Professor Andri and his colleagues for their kind invitation to visit People's Friendship University and University to deliver talks in their seminars and for a possible scientific collaboration. So please allow me to introduce myself briefly. My name is Амар Деббуш. I am professor of mathematics from Algeria, working in Gуэльма University. For research, I am working in both pure mathematics and applied mathematics. So the lecture of today for this seminar on differential and functional differential equations, it will be devoted to something related to pure mathematics. But after tomorrow, in my second lecture, it will be devoted to applied mathematics. Okay, today I will talk about some classes of abstract fractional control dynamic systems. The lecture of today divided into two parts. In the first one, we will study some analysis and approximate controllability for some stochastic non-local equations. So we are interested with the following Cauchy problem, system 1, 2, which is a non-local fractional stochastic system of Sobolev type. So our main purpose here is...
Sorry, I have a following question. You mean non-local? This means that
non-local condition. We have non-local condition here. Yes.
Because very often mathematicians consider fractional derivative as non-local operator.
No, I'm not.
I understand.
Okay, I am interested with the condition here.
And G,
so
G
if G is
non-linear function.
Not necessary. If G here is 0, it will be initial condition.
Yes, I
with
understand.
G, we have non-local condition. So x of 0, it will be considered as a function, not as a value. Okay? So our main purpose here is to study both existence and uniqueness solution together with the approximate controllability. For this, our main aim, we will need to realize the theory of fractional calculus first, second, stochastic analysis, third, semi-group theory, and the last one, fixed point techniques. So we need to define our problem. So dqc is here the Caputo fractional derivative of order q between 0, 1. Let our interval with this form such that B is finite. Let us consider x and y be two Hilbert space such that the state x takes its values in x. We assume that our operators L and M are defined on domains contained in the Banach space, Hilbert space X, and the ranges contained in Y. The control function U belongs to the space L2 gamma, which is a Hilbert space of admissible control functions with U as a Hilbert space. B is a linear bounded operators. F, G, and sigma are appropriate functions, abstract given functions, and x0, gamma 0 measurable x-valued random variables independent of W, which will be specified later. Here also we have gamma 0 and L2 0 and W will be defined later. Okay. Now in order to study the main results of this work, we start to review some preliminary results. We start by a short introduction in fractional calculus. We define here what we mean by a fractional integral in sense of Riemann-Liouville for alpha positive of a function f in the space L1. It given with this formula such that gamma is the usual gamma function, which is one of the special functions of fractional calculus. Now, if a takes 0, we can write this fractional integral as the convolution of these functions, g alpha and f, such that g alpha takes this form. And we have the limit of g alpha, this one, when alpha tends to 0, is the Dirac delta function. So this is the definition of what we mean by a fractional integral. Second, we define what we mean by a fractional derivatives. In fact, we have many sense for the fractional derivatives, and recently, in recent years, it was introduced many new senses, but unfortunately, most of them are wrong or with limited applications. But the most successful senses that shown successful applications are the sense of Riemann-Liouville and the sense of Caputo. Okay, the sense of Riemann-Liouville is given with this formula, where the fractional derivative alpha fractional order in this interval, given with this form, and the sense of Caputo derivative is given with this form. Here, when alpha between 0 and 1, this summation will be reduced to the initial function f of 0.
Tell me, please, I have a following question.
Okay.
Is it possible to define fractional derivative with the help of Fourier transform? If you have
With the
function
help
on the
of
Fourier
Fourier transform.
Fourier transform.
Yes, of course.
Yes, but in this case, is it equivalent definition to your?
Yes, equivalent,
okay,
yes, because it's integral transformation. Yes. When we apply its inverse, we can return to the origin.
I see.
Okay. So some years ago, I visited Voronezh State University. They told me that the sense of Caputo is originated. Its origin is by a scientist from Russia. Yes, his name is, I forget him now, but the sense of Caputo is originally from Russian scientists, and Caputo just improved it.
Нет, это Упругив академик.
I have his name, but now I forget only.
Kilbas?
No, not Kilbas, no. From,
Герасимов.
yes, this one, yes, this one, yes.
And is he from Voronezh?
No, colleagues
Because
from
he told
Voronezh told me.
something,
Yes.
They told you
Yes.
about this name. Okay.
Yes. Okay, we have a remark. So, if the function f of class Cn, though the last sense of Caputo can take this form. Also, we have the Caputo derivative of a constant is equal to 0, like the classical derivative, but this property is not satisfied with Riemann-Liouville, where the fractional derivative of Riemann-Liouville for a constant is a function. So this is one of the main differences between Riemann-Liouville and Caputo. Other remark, if f is an abstract function with values in a Banach space, so the previous integrals are taken in Banach sense. Okay, now in order to solve the Sobolev type questions, we need the following properties will be needed later. So we have both operators L and M are linear and M is closed. Second one, we have domain of L contained in domain of M, and L is bijective. the last one, L minus 1 defined as a pair is a linear compact operator. So this is needed to solve the Sobolev type question. Okay? So we have some properties too. From the last assumption on Sobolev type question, we did use that L minus 1 is bound operator, and for short, its norm can be a constant. From the same assumption, we have that L is closed since L minus 1 is closed and injective. So automatic, its inverse will be also closed. So it comes from our assumptions and the closed graph theorem. We obtain the bounds of the new composite operator ML minus 1 defined on Y with values into itself. So we can conclude that this new operator ML minus 1 generates a semigroup with this form. So in order to formulate later or construct a solution representation, we will need the theory of a semigroup. So our semigroup will take this form. We suppose that the supremum of its norm is finite. Okay. Now we just apply the fractional integral in sense of Riemann-Liouville on both sides of our considered problem, and we use the non-local condition. It is easy to get this equivalent integral equation. So this is an equivalent integral equation to our considered problem, but not yet a solution. Not yet a solution. Okay. Since we have stochastic term in our considered problem, so we will need some theory or some analysis from stochastic. So we will work, of course, inside probability, complete probability space, equipped with a normal filtration gamma t, which satisfying the usual condition. Okay. Also, we consider four real separable spaces X, Y, E, and capital U, and Q winner process on our probability space, this one, with the linear bounded covariance operator Q such that its trace is finite. We assume that there exists a complete orthonormal system with this sequence in E, also a bounded sequence of non-negative real numbers lambda n, such that this equality holds, and also a sequence beta n with this form of independent Brown motions such that it takes the following form. And gamma t with this form is the sigma algebra generated by this W, this which is the independent Brown motion.
Excuse me, what is gamma B? What's the difference between gamma and gamma B?
Gamma B is the final point in our interval gamma here, which is a normal filtration gamma t, and B is the final point of our interval. Yes.
Okay.
Okay. Also, let L2 0 with this form be the space of Hilbert-Schmidt operators from this space to the whole Banach space capital X with the inner product, this one. And let L2 of this form be the Banach space of all gamma B measurable square integrable random variables. We work inside random variables because stochastic process is a special case from random variable. Okay, with values in the Hilbert space, this one. Let capital E denote the expectation with respect to the measure P. And let C with this form be the Hilbert space of continuous maps from G into L2 satisfying this inequality. The supremum of this expectation is finite. Now let H2 with this form is a closed subspace of C with this form consisting of measurable and gamma T adapted X valid properties with this form, x in this space, endowed with this norm, as you see. So this is just some definitions in stochastic analysis to be used later for our main results. So we start with our first auxiliary results that will be needed for the main result. So this relation between stochastic term and deterministic term. So let capital G with this form be a strongly measurable mapping such that the integral of this expectation is finite. So we will have this relation that will be needed later to estimate our solution. As we said, this is a relation, very important relation between stochastic and deterministic differential for all t in our interval and p greater than or equal to, where Lg here is a constant involving on both p and b. Okay. So you can stop me anytime to ask any question, no problem. So now definition, we define now what we mean by a mild solution of our considered problem. So a stochastic process x in H2 space is a mild solution of our considered problem if for each control u in this space, it satisfies the following integral equation, number 4. So this is a solution. Comes from the previous equivalent integral equation, where both capital S and capital T are characteristic operator given by the following forms in terms of C0 semi-group, S of T, C0 semi-group, or we say strongly continuous semi-group. And here we have which generated by this composite operator ML-1. And zeta q is a probability density function defined on this interval satisfying the following conditions. Okay. So this is the definition of the mild solution of our problem. Now second auxiliary result, we have both characteristic operator capital S and capital T are strongly continuous, means that the following mathematical properties satisfied. Now in order to study the existence and uniqueness of solution, we need to construct sufficient set of conditions. We start by the first one. We assume that our characteristic operator capital T and capital S are bounded linear operator. It means the following inequalities are satisfied. The second one, assume that F sigma with this form and G satisfy linear Groth-Lipschitz conditions, and the following inequalities are satisfied for our estimations later. And the third one, the linear stochastic system is approximately controllable. Okay, now we try to define the controllability operator. So for each t in this interval, the operator, this one, tends to 0 in the strong operator topology as alpha tends to 0 plus, where the controllability operator, this one, is in stochastic case named as controllability Gramian operator, for which B star denotes the adjoint of B and T star denotes the adjoint operator of characteristic operator T. Okay, now we try to reduce our considered problem 1, 2 with the following 1, 5, 6. So this is linear fractional system without stochastic, as you see, in order to understand our theory. So this system, linear system, is approximately controllable if and only if we have necessary and sufficient condition that this operator converges to 0 strongly as alpha tends to 0 plus. So the approximate controllability for this linear fractional deterministic without stochastic deterministic control system 5-6 is in fact a natural generalization of the approximate controllability of linear first order control system when we have the fractional derivative Q1. The operator L of Sobolev type question is identity. So we just generalize the case here. Now we give a definition for the approximate controllability notion. So our considered system 1, 2 is approximately controllable on our interval G if the set R of B is dense in L2, where R of B with this takes this form. B is the final point in our interval, and U is our control function. Here L2 gamma is the closed subspace of this one, constructed of all gamma T adapted U-valued stochastic process. Okay. The next auxiliary result. So for any x b tiled in this L2 space, there exists phi tiled in this space such that this equation is satisfied in terms of this expectation and the stochastic term. Okay. Now for any alpha positive and x pi tiled, we try to give the exact formula for the control function in our problem in terms of the controllability operator. So it's given with this formula. So this is the formula of the control function in terms of this controllability operator. Other auxiliary result. So there exist two constants with these notations such that the following estimations in terms of expectation are satisfied. So we can check them quickly. For the first one, for every 2 points in H2 from the Holder inequality and previous lemma, we can get our estimation such that this constant takes this form, and similar arguments for the second inequality. Okay, now we are in position to state and prove the main result of this talk. We start to prove that our problem has a unique solution. For that purpose, we define the operator F alpha from H2 into itself with this form, the same solution representation. So we transform our problem into fixed point technique with this form. Lemma 3.1, for any x in H2, we have F alpha x, this one, is continuous on our interval, but in L2 sense, Okay.
For here, I assume that the control U is positive.
Our control?
Yeah.
Yes, positive, yes. Mm-hmm. So, for the proof, we assume T1 and T2, two different points in our interval. Then we will, from our formula 9, the last one, so let's, this one. Okay, so we can have this estimation. On the right hand side we have 4 members. We try to estimate each member from the right hand side. We can check easily from our construct sufficient set that each member tends to 0 as T2 tends to T1. for the first member, second member. This is so simple calculus. So after that, we can use the strong continuity of this characteristic operator, Lebesgue's dominated convergence theorem. We conclude that the right-hand side tends to 0 as T2 tends to T1. So we conclude that f alpha x, our operator, this one, is continuous from the right of this interval. With the same arguments, we can have the continuity from the left side, and hence our required result. So the first main theorem now, assume that our assumptions, this one and this one, are satisfied, then our system has a mild solution. Okay? So we prove by using contraction principle mapping. So the operator f alpha, we use contraction mapping principle. First, we show that f alpha of H2 contained in H2. So we made our estimations like the previous one in terms of the following expectations. Okay, by using our auxiliary results. After that, we arrive that the expectation of this norm is finite. We can use lemma 3.1. We get that f alpha x belongs to H2. Thus, the operator f alpha maps H2 into itself. Next, we use Banach fixed point theorem to prove that f alpha has a unique fixed point in H2. So we will use this estimation again. We have 4 members. We use just...
Sorry, can Q be 1/2?
Sorry?
Can Q small be 1/2, 1 over 2?
Q,
Q small. But it's between 0 and
the
1?
fractional derivative, between 0 and 1.
Yeah, can it be 1 over 2? So, to multiply by Q minus 1.
A Q is the fractional derivative.
Yeah, Q small, yeah. Can this number be 1/2?
Yes, between 0 and 1.
But then
in the denominator we'll have 0.
Just a moment, please. Yes. I think here something is missing. No. In this case, Q is more cannot. Just a moment. I mentioned before. Just a moment. Q should be with some sufficient condition. We have sufficient condition before. What?
Definitely smaller than 1 over 2. Otherwise, it won't.
Yes. There is sufficient condition before. I forget it only.
Even greater than 1 over 2.
Yes. There is sufficient condition before. Yes.
And the 2 should be greater than 1 over 2.
Yes. Okay.
So greater or smaller?
No, it's greater.
Greater.
Yes. Okay. So we can check these inequalities. Okay. And after that, we can arrive that our operator f and alpha is a contraction mapping, so that the contraction principle ensures that this operator has a unique fixed point. This fixed point, in fact, is a solution, a mild solution of our considered system. Okay. Now the second main theorem about the approximate controllability. Assume that our assumptions hold. Further, if the function f and sigma are uniformly bounded and the characteristic operator capital T is compact, then our system is approximately controllable. So for the proof, let x alpha be a fixed point of our operator f alpha. So we use the stochastic Fibonacci theorem. We can have that x alpha of b takes this form. Yes, x alpha here is a state function at the final point of our interval b to have the controllability, approximate controllability. Okay, so from our assumptions, previous assumptions, we can have this estimation. So this summation can be estimated by this constant, which is positive. Then we can conclude that there exists a subsequence still denoted by the same notations, the following ones, which converges in weak sense to the following functions in these spaces. Okay, so from above properties and assumption 3, the last one, we have for every s in this interval, this operator converges to 0 strongly as alpha converges to 0 plus. And moreover, we have the norm of this operator is estimated by 1, bounded by 1. Thus, we can apply Lebesgue's dominated convergence theorem and the compactness of both characteristic operator S and T to get this needed property. And hence,
We have S is a sort of time, right?
yes, S is the time here.
So it means it's not only condition on F, it's also condition on the X itself. Because X alpha S F, probably it should be smaller than D.
Here we have the solution depends on the control function.
Yeah.
Yes.
So it means that, and also depends on the right hand side, so it is a little quite complicated. This condition 15 is.
It's not a condition.
At the initial moment I understood, but then you move further, then you assume that it is at the initial moment it's small, then it will maintain small, but time.
Here trying to apply Bolzano-Weierstrass criteria to subtract subsequences still denoted by the same notation to have our convergence. We need the convergence of
Depend on T. You have convergence, but for any fixed time T. But as T converges to infinity, this convergence will become weaker and weaker.
No, here all the business on the finite interval only.
Only
There will be-
finite,
Yeah.
Yes.
Yeah.
It's not infinite interval. The time interval is finite.
finite, yes.
So it's not for T converges to infinity.
No. Our time is finite here. Yes, B is the last point is finite. And after that, we will have to approximate controllability. So this is the end of this part. So I would like to move the second part of this lecture. If you don't have discussion about the first part.
But still I have the same question.
Okay.
So time T is fixed, but as time T converges to T capital, X alpha can reach values that exist constantly star.
We will not have the approximate controllability when T tends to when the time tends to infinity.
So
Our dynamic.
every time, so it depends on.
Our dynamic system should be fixed by 2 points. The first one is 0 and the last one is finite. How we can control some dynamics on infinity?
From assumption F exists D star such that this is for all S is a closed interval. Probably closed interval.
Yes.
Is closed interval?
Yes, closed interval. Yes.
Okay, thank you. We mentioned that U is a positive function, but is it really a scalar function in your model? Can you show the first slide with the statement?
Which one?
Yeah. So, is U a scalar function or not?
Which one?
U.
U is a control function.
Is the scalar function a vector function?
So we mentioned that U is a positive function, but what does?
Yes,
What does it
positive.
What if it takes values in Hilbert space?
I don't understand exactly the question.
You mean not unbounded? It's positive but unbounded?
Is U a scalar function or?
Here our semi-group theory, we use the strongly continuous semi-group. T should be positive, T more than or equal 0 only. And T is the time here. The control depends on T and the state function X depends on T. So T is positive here.
What is the range of U?
Of U.
What of U?
U belongs to the set of admissible control functions.
It means the range of a fixed function U from this admissible set.
The function U.
Does it take values in R1
Sorry.
or R2, R3? In which space?
U belongs to this space L2 gamma, which is a Hilbert space of admissible control functions. And this range is also a Hilbert space.
What does the positivity of U mean?
Positivity of control. We control some dynamical system in the semi-positive axis.
So the question maybe is what is U capital? Is it
A Hilbert space.
It's a Hilbert space.
Yes.
and B is the bounded king operator and Hilbert space is unbounded or it is so normal is
So you ask, is U positive?
It is positive and belongs to Hilbert space and Hilbert space is normal Hilbert space is bounded
Yeah, let's keep it.
by constant which is dependent on
Maybe later we will discuss it with details.
Нет, гипотетическое пространство у него ограничено и фиксировано константой. No, U is positive. But so
If U is not a number,
Узначная функция, что значит?
да, не знаю. Спасибо.
okay, let us discuss it.
Later, okay. Can I please move to the second?
Что, на доске?
Не-не-не, второй факт. Доклад разбит на два.
Sorry, my second part didn't include a slide, so I will try to try my own.
Okay.
Or maybe like this.
You have a lot of black box at your disposal.
I think it's not very clear.
По ширине экрана.
Yes, yes. Yes. If you don't mind, help me from there, please. Okay. So return to the title, please. So in the second part of this lecture, we will talk about some solvability and optimal control problem for impulsive non-linear fractional inclusion. So the previous part related to fractional equation, and the second one it will be related to fractional inclusion now. In the first part, we used non-local condition. Now we will use impulsive condition. Okay? Please move. Okay, so we are interested with the following control: fractional delay, differential inclusion of the following type, following form. So here we have differential inclusion. Okay. Delta alpha B denotes the Hilbert fractional derivative of order alpha and type beta, where alpha has chosen here between half and 1, and type beta in this closed interval. Okay. We assume that the operator A is the infinitesimal generator of strongly continuous semigroup C0 semigroup S of T on Banach space capital X, and B, as usual, is a bounded linear operator from a separable reflexive Banach space capital Y into X. Okay. Partial G here is the Clark's subdifferential of G. Okay. And F is a multivariate map. So T here defined on this sub open interval 0B without minus T1 till Tm. It means that our state function X is not defined on T1, T2 till Tm. We have jumps here. We have here our initial condition given with this form, and our impulsive condition is given with this form. UAD is the set of admissible control functions. Okay. XTI plus and XTI minus are the right and the left limits of X at the points Ti respectively. UAD already mentioned is the set of admissible control functions, and let capital A AD be a set of all admissible both state and control, state X and control pairs. Okay, please. And we present the cost functional. And we present the cost functional with this form. We have discrete forms here because the state function is not defined on the point T1 till Tm. Okay. So our motivation here, can you return please to the main problem? Return please. So here we considered the multivariate, since we have here differential inclusion, we will use the theory of multivariate maps. So capital F is a multivariate map given in terms of delay argument delta, and the Clark subdifferential partial G is also given in terms of delay argument delta. Okay. And we will use the advantage of impulsive condition, where the state is not defined in some limited points in our interval. So this is our motivation. Okay, please. So in order to get the main results of this work, as usual, we mention or we review some preliminary results. We start by the fractional calculus. So we already defined what we mean by a fractional integral. Please move. And also we defined what we mean by Riemann-Liouville fractional derivative and what does mean Caputo fractional derivative. And now we define our used fractional derivative here, which is a Hilbert fractional derivative of order alpha between 0 and 1 and type beta in this closed interval that given with this form, as you see, this one. Okay, so this is the Hilfer fractional derivative for a function f. We have a remark here. If beta, the type beta is 0, alpha between 0, 1, and a is 0, so the Hilfer fractional derivative will be reduced to the Riemann-Liouville fractional derivative. Okay? Now, if the type beta, here 0, if the type beta is 1, and alpha in 0, 1, a 0, so the Hilfer fractional derivative here will be reduced to the Caputo derivative with this form. So, we can see that Hilfer fractional derivative is considered as an interpolator or a generalization of both Riemann-Liouville and Caputo sense. So, for special case, Hilfer can be reduced to Riemann-Liouville, and other special case, Hilfer reduced to Caputo. Okay? And now we define what the notion of a Clark subdifferential. Okay? Let X be a Banach space with dual space X star, and G with this defined as appear be a locally Lipschitz functional on X. So the Clark's generalized directional derivative of G at the point X from our Banach space in the direction Z in the same Banach space, denoted by this notation, is defined with this form. Okay, G0 is defined with this form. Now what does mean Clark's subdifferential? So the Clark's generalized gradient of G at point X in capital X, denoted by this notation, partial G, is a subset of X star, this one, given by this form that you see. So this is what does mean Clark subdifferential. Okay. Okay. In our work, so we will, since we have implicit conditions, so we will need to work inside this space PC, which is the space of X valued bounded functions on our interval G with the uniform norm, this one, given by this form, such that xti plus, as we said previously, the state X is not defined on T1 till Tm, such that xti plus exists for any I from 0 to m, and X is continuous on these sub-intervals from 0 to m, where each sub-interval is given with this form. And T0, the first point of our interval, is 0, and the last point B is Tm plus 1. Okay? Please return one. Okay. Okay. So, in our considered problem, we have mentioned 1 minus alpha times 1 minus beta. Alpha is the Hilfer derivative and beta is the time. So this part will be reduced as 1 minus q. 1 minus q, such that q takes this part in terms of both alpha and beta. So now we will work in a specific space from this one, called PC 1 minus q. 1 minus q, that depends on both fractional derivative and the type beta. PC 1 minus q, which is defined with this form, the space of all vectors or all states X, such that this condition holds. Okay, with the norm, with the norm denoted by this notation, which defined as the maximum of the supremum of this set. We can check easily that this our new space is a Banach space. Okay, Now?
I'm sorry, but
Okay.
it remains only 1 minute.
Sorry?
It remains only 1 minute.
Oh, to finish, we
Yes,
just...
because this
Okay.
room will be occupied after
Ah, okay, sorry
our
for that.
lecture. But we can discuss this.
Okay. So we can skip. So usually, okay, no problem. I was thinking that 1 hour is presentation, then more time for discussion.
For the
Okay.
discussion, it will be in my office,
Okay, okay.
having tea at
Yes,
the same
okay.
time. And
So in order to get our results, we will need the theory from multivariate map, and we will use distance in sense of Hausdorff. Okay, please move. And we have some properties from the multivariate maps also here. Okay, please. We will use this Sadowski's fixed point theorem to guarantee the existence. Again, please. And okay, just a moment. In order to formulate a solution representation for our considered problem, we will need to use this right function, which is one of the main special functions of fractional calculus that given with this form, satisfying this equality. After that, we define what we mean by a mild solution of our considered problem. So a pair of functions, state and control, in this space is called a mild solution if the following conditions satisfied: initial condition, implicit condition, and this condition. Just a moment. And the following integral equations are satisfied. As we see here in the first subinterval 0 t1, we don't have here implicit condition. We have only initial condition and implicit condition starting from the second interval to the last one. Okay, so in the first subinterval 0 t1, we have only initial condition and the non-local condition, if any. If we have non-local condition, it will be here. But implicit conditions start from the second subinterval to the last one, because we have jump on each isolated point or singularity point. Okay, here we have some properties to be used. The semi-group should be continuous in the uniform operator topology and satisfy the following condition. Our characteristic operator satisfying some properties. I think time is finished. We need to respect the rule.
Okay, thank you very much for
Okay.
interesting lecture. And do colleagues have any questions? Okay, then if there are no questions or no questions took place during lecture, then let's thank our speaker again. And now I invite